everyone, my name is Patryk Kowalski and I work as a senior machine learning engineer at deepsense AI. Today I'd like to talk to you about the R in RAG, which stands for the retrieval in the retrieval augmented generation, and I intend to give you some practical tips for improving your retrieval results. Let me tell you that it's very fitting that I get to talk about this on the Valentine's Day, because I will be sharing my love for all kinds of retrievers, not only golden retrievers, but also the retrievals for your RAG systems. Okay, and I am aware that most of you have probably heard about RAG systems already on more than one occasion, because it's not very easy to not have heard about it, but I still believe that you should tune in and listen to what I have to say, because I am able to share with you a commercial experience that I got in building retrieval in deepsense AI. All right, so what we're going to be talking about is what the retrieval augmented generation is in general and what it's used for, about its components, which are embeddings and the vector databases, about how to configure those components, about how to measure results of your retrieval once you get it running, about what you should focus on to get the best results. This is actually my favorite part. This is the hands-on experience that I can share with you of what is the most important to get really good results and not work very hard on it. And then we'll go to the summary. So starting with the retrieval augmented generation. The idea is that you want to be able to chat with your data, but you do not want to have to train a model in order to do so. You do not want to train a model every time you want it to be anchored in your domain knowledge, because it requires know-how, it's not easy, it's expensive, and because the model fine-tuned in your data still can hallucinate. If you use a retrieval augmented generation system, you're able to reduce the hallucinations because you make the model only use the context that it's provided. So you use the retrieved information from your company documents or your dataset in general, and you can find the pieces of information that are most similar to a user query that user is asking about, and you can stuff this information into the context of a generative model that will be answering the questions. Another perk of this system is that the knowledge base is dynamic, which means if something changes in your company documents, you do not have to change anything about your system. You just swap the documents in your vector database, where if you use the fine-tuned model, you would probably have to train it again to make it switch to the new knowledge. And something very important in RAG is that it is able to provide citations for your user, so it doesn't have to trust blindly that what your model the response of your model was correct, because it has a source and it has citations to validate the answer. And today we will focus on the embeddings and vector databases part, because these are the components of retrieval I want to focus on. So first thing you gotta do, if you want to use your company data inside such a system, is to create embeddings. Embeddings encapsulate meaning of sentences inside a numeric vector. So this way it's easier to process, to compare, to find similar pieces of information. And in order to create an embedding, you need a proper embedding model. By proper embedding model, I mean a model that is suitable for what you want to do. So you need to look at things like what languages does it support? Is it English only, or do you require more languages? What is the size of the context the model can embed? Or perhaps do you care about thresholding the similarity score of embeddings that you get from this model? Because some models are better at varying the similarity score between very similar pairs of sentences and not such similar, and others are pretty set on returning high similarity scores for everything. And in order to embed a piece of text, you need to split your document using a text splitter to make it fit in the embedding model context. There is a number of parameters for a text splitter, such as chunk size, which is how big of a piece of text one chunk should be. which is overlap, which means how many common characters do you have between two adjacent chunks. And you should probably decide on a structure, whether you like a simple flat structure of just each chunk being as important, or maybe some more hierarchical structure with, for example, parent chunks and child chunks, which we'll get to in a couple of minutes. And the easiest text splitter you could come up with is a character text splitter, where you decide on some separator. Typically, it would be an empty string, and you just stuff text inside the chunk until either you meet the separator or you go out of your chunk size. That's a very simple idea, but it can be a bit better if we do this recursively, which means that we propose a number of separators. For example, our favorite way to split text would be on paragraphs, but if we cannot split on paragraph because it's too big, then we can split on new line or on column. So this way, the chunk you get is more likely to be semantically homogeneous and to only contain one topic. And if you have some particular structure of your data, like HTML or Markdown documents, you can, of course, reflect that in the sequence of separators you choose. So you can use HTML or Markdown tags or like headers, etc. And there is one fairly new idea to already split the text semantically, which means you embed the text sentence by sentence. You measure the similarity of one sentence next to the other, and once you reach a peak of difference, so you find significantly different sentences, this is the place where you would like to stop one chunk and start another one. So this seems like a really good idea. Haven't tried that in practice yet, but it seems like it would work nicely. And all of those are actually in LangChain if you want to import the library and just use them. So to have a little summary at this point, in order to prepare your documents for retrieval augmented generation, and you do want to prepare your documents correctly, that's an important step. If you put enough effort in processing your data at this point, your LLM will read it like an open book. You want to select a proper embedding model with parameters of the embedding model, and you want to split your data in a meaningful way. Again, with the parameters like chunk size, overlap, or the chunk structure. Once we have our embeddings, so we've managed to change our text documents to like vector representations, we need to store them somewhere, and that's what vector database is for. The idea isn't very complex, but you typically don't want to build it from ground up because there's a number of existing implementations already, and a lot of them are open source, so there's really no reason not to use them. What vector databases do is, for one, they do store embeddings, any number of them, really. It can be a very big database. It does index the embeddings, so they are easier to search, to sift through your vectors. And yeah, mostly that. And a good vector database will do this efficiently. You may be wondering how to select a vector database, because since I said there is already a number of them on the market, you can use some comparison, like the one I have linked here at the bottom of the slide. Typically, the attributes you will want to look at when making your decision is, for one, the license, because it needs to be aligned with the kind of project you want to do. Does it need to be open source? Do you need to have it on premise? You will care about supported search algorithms. We'll talk about that in more detail in a couple of minutes, but basically you will want to have some kind of sparse search algorithm, some kind of dense search, and if you're really lucky, a hybrid search algorithm that can combine them. You have to decide whether you care about a managed instance, so whether you want to host it yourself or perhaps you want to offload it to the provider of the vector database. You may want to figure out what kind of frameworks you want to do and integrate with, because if your whole application, for example, is in LangChain, or in llama index, you will want your vector database to integrate with that as well. And you may care about what kind of indexing it supports, because depending on the kind of your use case and data, you will want a different index. I have heard rumors that OpenAI and Anthropic, for example, use Quadrant vector database. So perhaps they do something better than the others. Although, for example, I do have the most experience with the V8 vector database, which is why I will use it as an example to show you how you can configure it from scratch. So if you would want to go with V8, it's really easy to configure, like the first running version, because they provide a configurator. You just have to click on the modules you're interested in, and the most important modules will be what kind of vectorizer you require, by which I mean the embedding model, whether you want to host it yourself or maybe use an API like for the OpenAI models. And if you do want to host it yourself, whether you want to use a pre-built image from V8, they have a big list of pre-built images, so that's most often what you want to do. But if you have some more niche model you want to try, you can always build an image, and as long as it's compatible with the Hugging Faces auto model, you're good to go. And another module of interest would be a re-ranker. That will typically be a cross-encoder model that helps you order your retrieval results correctly from the most probable to contain useful information to the least probable. And once you select all of those, the configurator will create a Docker Compose or a Kubernetes Helm file for you that you can use to start up your vector database. You will need to select an index. V8 offers two kinds of indices, the default one being the HNSW, which stands for Hierarchical Navigable Small Worlds. This is a complex index that is slower to build, but it scales well to large datasets as queries have a logarithmic time complexity. So I'm not going to get into how it works because it's quite complex, but like the general gist is that you have a multi-layered graph where the higher you go, the higher layer you go, the more averaged vectors are, centroids. And whenever you have a query that is embedded, you start at the top with the rough ideas of vectors, and you traverse the graph to the bottom to find the most similar vector to your user's query. And you can also go with flat indexing, which is the right choice when perfect accuracy is required and speed is not a consideration. So basically for small datasets. About search methods, V8 offers full text search method, which will most typically be used for filtering properties, by which I mean you may have some metadata with your documents, like some kind of tag, for example, and sometimes you will only want to find information that is tagged this way. So then you want to do a full text exact match search. So that's what it's good for. And you will have some sparse, based on word frequency, search method, like BM25 in case of V8. And they also call it the keyword search. So you may wonder why is it important? Because typically you care more about the dense search, the vector search, because it has the semantic similarity. This is the main feature of the similarity search, but there are cases where the keyword search is also very important. One thing that comes to mind is if you would have a number of instruction manuals for some, I don't know, factory components. The instruction manuals tend to be very similar from one part to the other, with similar instructions, I guess, but what makes them different is the actual keyword of like the number of the component you care about, and it's pretty crucial to return the correct manual page. So that's when you care about the keyword search, for example. And you will typically want to use the hybrid search, which does combine both the sparse and the dense search methods. You can use, in case of V8, the alpha parameter to regulate which one is more important. And what hybrid search does, it runs both of those searches and then combines them together to find the most relevant piece of information. One caveat you should have in mind is that hybrid search can make scores hard to interpret due to the score fusion mechanism. So even if the initial similarity score you would get from, for example, your dense vector search is thresholdable. So like 0.9 means good information, 0.3 means bad information. After combining it with the sparse vector search, the scores get rescaled, and it can trip up your thresholding. So at this point, you will get results, but you want to only get relevant results. So you need to cut them off at some point. You need to set a limit of retrieved chunks. And if you set too low a limit, if you have not enough pieces of information, you can miss information, obviously. And if you use too many chunks, that's not good as well, because you will bloat the LLM context. There will be too much information. It will be confusing. So Weaviate helps here. When you're feeling indecisive, you can go with the AutoCut feature. In their own words, AutoCut aims approximate where a user would cut the results intuitively after observing and jumps in the distance from the query. So ideas similar as in the semantic text splitter, where you look at the next and next and next distance, and after you observe a peak, you cut off at this point. And again, if you do use hybrid search, then the distances in the similarity scores can get a bit messy due to the score fusion. Weaviate claims that if you use the relative score fusion algorithm instead of ranked fusion, it will work well with AutoCut because of the natural clusters that AutoCut can detect. But still, I advise you to check that if you want to use AutoCut with hybrid search, and make sure that it is actually the case in your case. And once you get results, you may get a correct number of results, like 5 chunks. That's what you want to have. You care about having them in the correct order, because LLM may be most likely to look at the first piece of information first, for example. Or you may want to take a shortcut and as your citation for your RAG system, always return the first chunk you get. So in this case, you really do care that the first chunk, the first piece of information you get, is the most important one. So we can use a cross-encoder. On a limited result set, you can afford a more computationally expensive approach. So use a cross-encoder to reorder your returned chunks paired with the user query to make sure that the most important is first. And as I said before, for certain embedding models, similarity scores won't be meaningful. And the cross-encoder scores will typically be meaningful, by which I mean easier to threshold. Like it will constantly be high for good pairs and lower for bad pairs. So a second meta summary. If you want to set up your vector database, you first need to select a provider. You typically can't go wrong at this stage because most of them do have everything you need, but still you should pick the one that suits you the most. You need to configure your vector database, configure all the parameters like the limit or the search algorithm. And at the end, you may want to use reordering and trimming your results, by which I mean the limit of chunks retrieved and the re-ranker. Well-adjusted retrieval will force-fit your large language model with useful context and ensure you get a good response. So we have all those parameters that you have to adjust, but you need to know when they work correctly and when they don't. So we do need some kind of metric, some kind of score. I would like to pitch a mean average precision score to you here. I like it. It works well because it only scores high if relevant documents are first on the list. So it not only cares about retrieving the correct documents, but also retrieving the correct order of documents. And let's go through how it works. Let's say a user has some kind of query 1, I called it, and a retriever retrieves 5 documents from the database that are supposed to be similar or related to this query. We check relevance because that's our test, so we know if the documents are relevant, and we see that the first 2 are relevant, but the 3rd and 5th one are not. So we need to calculate the precision at k for each one of those documents. So the first one is correct, so it's 1 over 1, 1. The second one is correct, precision is still 1. The third one is incorrect, so that's 2 out of 3, 0.67, and so on. We need to check the relevance. This one is easy. 1 if it's relevant, 0 if it's not relevant. And then we do multiply those metrics So for the first document, it's 1. For the second one, it's 1. For the third one, it's 0, because 0.67 precision times relevance 0, and so on until we go through all the retrieved documents. This way, we can calculate the average precision after we sum all of them up and divide by the number of relevant documents that were possible to retrieve. That's your average precision for a single query, and after you run it for multiple queries, you get mean average precision. And this is a good metric of how good of a retriever you manage to build. It's not always that straightforward, though, because you may notice that in this case, I assumed that if the correct document was retrieved, then it's all good. But in actual use cases, when you do optimize, for example, chunk size, it may not always be obvious if the correct chunk was retrieved, because let's say you have built a data set, so you have some ground truths for each query that you know you want to be retrieved, but because you sweep through different splitters and different chunk sizes, it may be that you retrieved only half of the ground truth because the chunk was, for example, split the ground truth in half. So then you need to decide if it is still a correct retrieval or not. And that's specific to your use case. The metric is easy to modify to allow for such cases. For example, you can modify the relevance to allow for more than 0 or 1, to not be binary. So it is also possible that one chunk you retrieved actually does retrieve 2 ground truths, in which case you may want the relevance to be equal to 2. So it would modify this metric, but it would still work well in comparing different retrieval configurations. So to sum up, you need to consider what is relevant for your use case, build the dataset with ground truths accordingly, and if necessary, modify the metric. And my favorite part now, what can you focus on to get the best results easily? So one of my favorites is the multi-query with the reciprocal ranked fusion algorithm. So one of the issues is that embedding models may not be very stable or not be very robust, by which I mean a slightly differently phrased question by the user may result in a very different set of retrieved chunks, set of similarities. So what you can do to remedy that is create a number of queries each time. So whenever you get a query, you create a number of alternative modified similar queries. You run the retrieval for each one of them, and then you mix them together using the reciprocal ranked fusion algorithm. You can create the alternative queries in a number of ways. If you want to, you can use an LLM to rephrase the queries. That would work the best, probably. But if you really care about efficiency, for example, or you want it to be really fast, or you do not want to have another call to the LLM, you can do something simple, like modify your queries by adding typos. And it's supposed to increase solution stability and increase robustness to imperfect user queries. And it actually does do that. And about the reciprocal ranked fusion algorithm, I like it because it takes into account how frequently a document is retrieved. So if one document is retrieved for more than one version of the query, it's good. And how highly scored a document is. So it looks at how highly scored it was for each one of those alternative queries. Another thing you can do is the hierarchical chunking. So you may have trouble deciding whether you want your chunks to be big or small. Small chunks make meaningful embeddings. Small chunks keep the generative model context from bloating, so it may be easier to answer. But at the same time, big chunks decrease risk of dropping information. They offer more context, but it will be slower. They increase response time because there's more tokens to work through. So what should you choose? You can go with some kind of hierarchical chunking, where you first create very big chunks. We can call them parent chunks from the original document. The chunks too big to embed them, too many tokens to fit inside the context. But it doesn't matter because you do not want to embed them. You want to split each parent chunk into a number of child chunks, and this is what you embed, the child chunks. And then when running retrieval, you do retrieve the child chunks, but you can decide to swap the child chunk for a parent chunk at any time. In particular, you may want to set some kind of parameter that, for example, if a parent chunk has 10 child chunks associated, you need to retrieve half of them. So the retriever needs to retrieve 5 child chunks, and then you do the swap for the parent chunk. It tends to work really well. So small chunks by default, but big chunks if multiple small chunks were retrieved. And one extra slide about accurate citations. That's a bit harder to talk about because there is no silver bullet at this point. You want to get citations because you want to be sure that your model doesn't make stuff up and obviously doesn't lie in production. And to do that, you may just use retrieval results directly, for example. So if your retrieval and your re-ranking works really well, then more often than not, the first chunk you get, the most similar one to the query, will be the best one. And you can just return it as the citation. It tends to work more often than not. But if you want something more sophisticated, you can use, for example, OpenAI function calling, where you define a function for the GPT, where it not only has to answer the question, but it answers with a JSON dictionary, where one key is the answer, and another key is the index of the chunk it used, for example. And another idea to achieve the same thing would be to use direct prompting, to have a few-shot prompt for your model where you show it that it answers, and it provides the index of the citation of the source that it used for its answer. And it can either work really well or really badly. Depends on, well, what model you are using, for one, the size of the model, but also it very much depends on the quality of your data set. So if your data set is dirty, if, for example, it's been PDFs that's been OCR'd and have lots of like watermarks or like random numbers inside, it will mess up the numbering of the citations, it will mess up the indexing, and it will make it very hard for the model to actually pinpoint which citation it used. You may want to make it return actual text to cite it verbatim, but it's also not going to work greatly because the model will tend to rephrase it. So depending, you should probably try that, but depending on your data set, it's not always going to work great. Another idea from LangChain is to post-process all your retrieved chunks so hard to compress the content that you can retrieve and return all of them as the citation. So that the source content is already minimal enough that we don't need the model to cite specific sources or spans because we do provide all the sources. That seems a bit risky to me, but that's one of the things that LangChain does propose. Okay, so we have reached the summary. When you will decide that you want to build a retrieval augmented search, retrieval augmented generation system, you will need to select an embedding model and a vector database provider that suit your needs. You will need to select a text splitter and a chunk structure. You will need to select retrieval metric and prepare a dataset with ground truths for testing. And you will need to do a thorough optimization of all the parameters of retrieval, of splitting, of all of those parts to make sure that they work the best for your case. And I do advise that you pay extra attention to hierarchical chunking and multi-querying, because that's not a lot of work to get that running, and they tend to make your results much greater. Okay, so that was all. Again, my name is Patryk Kowalski, and I was talking to you about RAG, Retrieval Augmented Generation. Thank you.